This is my identity card. My name is Priyanka. I will tell you about the hack CPU. Before beginning with that, I would like to tell you about the hack computer. So let's begin. In the case of hack computer, we have a ROM 32K, we have a CPU, we have a data memory, and ROM 32K is nothing but the instruction memory. We have a PC over here which is taking the output from the data memory, the monitor basically, and we have a keyboard over here which is providing the input into the data memory. We have a ROM 32K which is taking the input from the PC, which is a program counter, moving on to the next instruction. That's what a program counter does. The instruction is then provided to the CPU. We have a reset pin in the CPU. The CPU is also taking the input from the data memory, which is in this case is in M. Now the CPU is generating the output. We got a write M, which is serving as the load pin for the data memory, which if it is 1, then the data instruction happens, otherwise you won't be able to see anything on it. Now, what types of instruction, what value of instruction, basically that deals with the out memory, which is of 16-bit, and write M is of 1-bit. We also have an address memory, like where we want to store the value. It depends on the address memory is in it. Now, what is hack computer? Basically, hack computer is a 6-bit computer architecture which is nothing but designed to make it simpler for the beginner to learn how does a computer works basically. Now, moving on to the main topic of our today's video. Now, the hack CPU, before diving deep into that, the implementation, I would like to tell you about the two types of instruction. We have an A instruction and a C instruction. A instruction deals with the address. The syntax for A instruction is at the rate value, and these in case of the C instruction, we got three types of things. We have a computation, we have a destination, and a jump. Now we also have a control flow which tells you about what the next instruction is going to be. That is done with the help of the program counter. Now let's talk about a little bit more about the A instruction and C instruction. So if you could look into this, we have a 16-bit instruction. The leftmost bit, which is most significant bit, that what you call it, and the leftmost bit is the opcode. When it is 0, it's A instruction, and when it is 1, it's the C instruction. Now, if you could look closely into that, in the C instruction we have A bit, and what does it deals? It basically tells you when which register to be selected, A or M. If you look into this table, we have when A is 0, A is selected. When A is 1, we have M, and we are dealing with D. So if you know about the ALU, we have X and Y. X is always D and Y keeps on changing. It depends on this A bit, whether it would be A or it would be M. Now let's look into this table. It's nothing but different type of computation would end up giving you different types of results, and same goes with different combinations of the destination bit will end up giving you different results. So is with the jump. Now over here I just wrote the full form of comp, which is computation. Dest means destination, and jump moving into the next instruction, which is basically dealt after the computation. Now I would like to tell you this is the complete chip, but before diving deep into that, I would like to divide it into small parts. So let's work this out. Learning about the A instruction design and how does that works. So we have a NOT gate. Now what does it basically do? It creates the flag, which could be A instruction or C instruction, depends on the current instruction 15th instruction bit. Now we have AND. What does this do? It decide whether the output from A should be loaded into the register output from the ALU should be loaded into the register, A register, and that and it also has the purpose. After that, it serves as the purpose of being the selection pin for the mux. Now, if we look closely into the diagram, I would like to draw something on it. If we look closely into the diagram, we have an ALU output which is serving as the input for the mux, and we have an instruction over here. Now this depends on this output. The selection pin depends on the ALU to A, which is given by the AND over here. So after the selection, we reach at this point. Now we have an OR gate. What does it do? It combines the instruction from this, as you could see, this, and the output from this. It combines the instruction and of these to load whether the A register, this register should be loaded or not. It decides, and after deciding that, we have an A register which tells what are we supposed to load into the A register. Now, so let's move on to the C instruction now. So here we have C instruction. We have reached a point over here. Now we are over here. Now we are provided with the A output. After this register, A register, we are provided with the by the A register output. We have another input for this mux. Here, this is from the memory, data memory. We have this thing over here, and we have another input from the A register. Now after this, the selection is done through the selection 12th bit, and that is what provided to this. Now we reached at this particular point. After this, we are dealing with AND. What does that AND do? That AND basically tells us about the D register, whether it has to take the output from the whether it has to take this ALU output. It decides that. Then this AND does that thing, and the D register, if we are talking about the D register, what does it do? It basically tells you whether we do have to load it or not. Now moving on to the ALU. So talking about the ALU, we have 6 different flags. As you could see over here, we have X and Y. These aren't the flags, these are the flags: X, ZX, NX, ZY, NY, F, no. These are the flags. So the flags which I'm talking about are nothing but the computation bits. Like if you look into that, will be the computation bit. It will be C1 and C2, C3, and up to C6. That's what the instructions are over here. And X, as I told you earlier, X is always going to be from the D register, and Y could be from A register, and that's why we have given the name A and M out. Now looking into this, after this decides whether the CPU writes the instruction in the data memory or not. So first OR gate decides the address, like what would be the address where we want the data value to be stored. The other OR bit decide what would be the value for the data memory, and the AND gate decides whether to write it or not. After that, we have control flow. Control flow is basically nothing but the program counter. It decides whether it has to jump or not. So we have different types of jump if equal to 0, which is decided by this AND gate, which we have jump if less than 0, this is decided by this gate, and so on. We got this. Now if we are looking into this, we have a PC over here, program counter. As we have already learned about the program counter, the most significant advantage given is to the reset. then the is the load, then comes the increment. So if the reset is 0, everything turns out to be 0. And this is how you design a CPU HDL code. Now let's talk about the pros and cons of the CPU. Let's come to the first one, simplicity and clarity. It's very simple as it's just another classic von Neumann architecture. Now talk about the basic functionality. We have done ALU, different control logics, program counter. It just deals with all those things. Now let's talk about the clear instruction. It's just a 16-bit architecture, so we have already done things with it. The flexibility, it's highly flexible. Now let's talk about the cons of the CPU. Now, limited explanation, it just doesn't explain it way properly, like what are the specific choices which we made in this and why we did so. The incomplete description, like using ALU out, ZR out, NG out, it's not explaining, like it's not getting deep into the ALU part. No clock mechanism. If we talk about the real world, we actually need a clock mechanism. It doesn't deal with that. Limited error handling. The design does not appear to have robust error handling mechanism. As in real world, error detection is like highly important, as what it deals with the invalid, how does it actually deals with the invalid instructions from the users. Now talking about the scalability and performance, it just deals with 16-bit instruction. What about the different ranges? It doesn't deal with those. Now the assumption, we have already assumed certain things about the RAM and ROM, and these are the external components. We have made the assumption regarding them. That could work for the small scale, but when we are dealing with a larger CPU which takes much more bigger instruction, it's not very good to deal with those things. So those were the pros and cons of the CPU, hack CPU. Thank you.